one more example of using Newton's second law. So we have a grindstone in the picture. It's a solid disc with a diameter of 0.51, mass of 50. It's rotating at 900 revolutions per minute. We press an axe against the rim with a force of 260 newtons, and the grindstone comes to rest in 7.9 seconds. Find the coefficient of friction between the axe and the grindstone. All right. So my grindstone, just drawing a picture from the edge. I know we're pushing inwards directly towards the center with the axe. This force is the 260 newtons they gave us. That's not the only force acting on the grindstone. The grindstone itself has a force of gravity, and we would draw that acting in the geometric center of the stone. There would be some sort of normal force from the axle that goes in here through the rotation axis that they've drawn. Out of these forces, we want to relate the forces again to time here. The weight, sorry, I don't mean to do all of these, whatever I'm doing. Hitting my screen the wrong way, so please forgive me. So the grindstone, to relate the force to time, is going to be through Newton's second law. The net torque by pushing in on the edge is going to cause the grindstone to slow down and stop. All right, so this force, though, the 260 newtons itself is not what's causing it to stop, right? Because that push is directly towards the center. The force that I neglected to draw is the force of friction. I don't know if you can see it, but very tiny in the picture, it shows omega. So this omega, the friction is going to be opposite, and it's going to be a kinetic friction because essentially the axe is sliding relative to the grindstone. So the only force causing a torque on this disc is friction. There's other forces, of course, but they're not producing torque, so they're not directly contributing to rotation. All right, so torque due to friction would be the lever arm, so line from the rotation axis out to the force, times the force, times the sine of the angle between them, but they're already perpendicular. The force of friction is acting tangent to the cylinder, the disc, and the radius goes out perpendicular to that. So this has to equal I. It tells us this is a solid disc. So going to the table, I would say this is 1/2 mr squared. So one of the r's cancels. So the friction force will be mr alpha over 2. In this case, we're trying to find the coefficient of friction. That's going to be within the friction force. We know friction can be written as the coefficient of friction times the normal force. So we will need to find alpha first. Now, one other side note, this normal force in our equation, this is the normal force at the edge of the disk where friction is actually occurring. It's not the normal force, not this one, in the picture overall, where we said that the disk has a normal force upwards from the axle that goes through the center. That's not the one we want. We need the normal force at the edge. Well, why is there friction? The friction is because we're pushing inwards with the axe. So that normal force at the edge is actually just the force we're pushing in at. It's the surface of the axe pushing inwards. Since I wrote it as F in my picture, I'm just going to go ahead and put F in my equation. So the other thing we need to find is this angular acceleration. We have the mass, we have the diameter, so we can figure out the radius. We just need to figure out alpha as well. All right, so once we get that, I'm just going to bring F to the other side. So that's ready to go. We can plug in numbers as soon as we figure out alpha. So coming back to the problem, it tells us this grindstone is rotating at 900 revolutions per minute. So that's an initial angular velocity or speed. We can convert that. We know 1 revolution is 2 pi radians. 1 minute is 60 seconds. So revolutions cancel, minutes cancel. So let's see, a 0 cancels, 2 becomes a 3, 3 goes into 9 3 times. So what, 30 pi radians per second. What else do we know about the motion? So we've pushed the axe against the rim. It comes to rest. So omega final is 0. And it does so in 7.9 seconds. Now again, we need alpha. So this one is 0. Alpha will be minus omega initial over time. Now the negative sign has to do with the direction. Right? Going back to the picture, if we could see that itty bitty teeny tiny omega on the original picture, getting a negative answer for alpha means omega, the angular velocity, and alpha, the angular acceleration, are opposite in direction. Which hopefully makes sense, right? If acceleration is opposite velocity, the object slows down. So angular acceleration being opposite the initial angular velocity, I'm sorry, this disk will slow down. Ultimately, when we come over to plug in for mu, if we plugged in omega initial over t, the negative, which is valid, we would end up getting a negative answer for mu, which is not valid. So if we think through this negative sign, hopefully it makes sense. Angular acceleration has to be opposite the velocity, the angular velocity specifically, to slow it down. Where the other negative sign is within this tension, the torque. The torque is in the direction of the angular acceleration. So technically, we have a negative sign in here already. And so if I carried that through, those negative signs will cancel. and we're going to get a positive answer for mu. It's also possible to just say the torque is positive and use the magnitude, the positive value of alpha, just put in the magnitude of it, because the change in velocity comes from this torque. So they have to be in the same direction. So let's go ahead and plug numbers in. So the mass is 50 kilograms. The radius of this disk is half of the diameter. Omega initial, this has to be in radians per second. That's why I have already converted it. The force of the axe pushing inwards, 260 newtons. And the time is 7.9 seconds. So let's see what we get here. I'm getting 0.29. And if we go with the significance of all the digits given in the problem, we would have 3 sig figs. So 0.293. Now, we should end up with no units. So in the numerator, I'm going to slide this just a little bit. Kilograms, meters, radians per second. Force is Newton, so kilogram meters per second squared. Let's see, so the kilograms are gone. The meters are gone. This cancels with 1. The other one cancels there. So essentially all we have left is radians, which again is not a true unit, so we won't write it down. We are getting an answer that has no units, and it's quite a bit less than 1. If you remember from when introducing friction force, the coefficient was typically between 0 and 1. So this seems reasonable. So relating forces to time, to motion in general, is through Newton's second law. Torque, the lever arm times the force, the perpendicular components. We get off the table or use the parallel axis theorem if we need to. And as long as the torque is constant and I is constant, then we can use the kinematic equations as well. We are going to talk about energy and momentum as well in relation to rotational motion. That's what the next videos will be about.